Welcome back, everyone, to the PENC Wilmington seminar. We hope that you enjoyed the first presentation today. We will take questions. There will be a point in the middle where we'll take questions, and then again at the end. So you can just type those into the question box, and I will read those out loud. Our next presenter is Scott Jennings. He is the Director of Area Operations with Duke Energy Progress in Wilmington. Mr. Jennings has nearly 20 years of experience in the electric utility industry with past responsibilities including design engineering, resource and project management, and operations. He began his career with SCE&G in Columbia, South Carolina, and then moved to Duke Energy in Charlotte, and then to the Wilmington area with Duke Energy in 2017. In his current position, he's responsible for all of the day-to-day operations of the electric distribution system in the Wilmington metro area, including engineering, construction, and maintenance. During major storm events, he serves as the planning section chief for the coastal zone of Duke Energy, which includes 16 counties and approximately 500,000 customer accounts in southeastern North Carolina. Scott, thanks for being with us.
All right, thanks, Katie. Appreciate that. Good morning, everybody, and appreciate the opportunity to participate in this seminar with you guys. So thank you, and happy to be here. So I've got this broken up, and we'll talk about a couple of different elements here over the next hour, starting with the restoration process following major storm events, how we prepare and how we restore power. And then we'll talk a little bit about things that we're doing at Duke around hardening our grid, strengthening our grid, building resiliency into the grid so that we can help to reduce the impacts of future major storm events. So with that, we'll just go ahead and dive in, and we'll start talking about first the restoration process. So how do we go about at Duke restoring power, preparing for that restoration process in major storm events? And of course, you know, for those of us here, particularly, I think most of this audience is here in southeastern North Carolina. We've had a lot of practice with this over the past several years. Dealing with most of these different stormy weather situations, from tropical systems, the thunderstorms and tornadoes, wind events, flooding extensively, of course. About the only thing we can't point to is the ice and snow here. But you know, aside from that, we have a lot of opportunity, you know, and have tested that out over the past 3 years with Hurricane Florence. 3 years ago, a near miss with Hurricane Dorian 2 years ago, and then Hurricane Isaias last year. We've had a lot of opportunity to put these processes to the test, and we'll kind of talk through what that looks like and how we go about preparing for and executing the restoration process following those kinds of major events. So as Katie alluded to into the introduction, just to give a little bit of geographic perspective to things, when we talk about our coastal zone footprint within Duke Energy, and you know, I'm going to really talk about kind of across that zone, how do we go about the restoration process. That includes 11 different local zone operation centers scattered out from the Fayetteville, Maxton, Lumberton areas all the way to the coast, from, you know, Morehead City and Beaufort down into the Wilmington metro area. So that's a pretty large geographic footprint. As Katie said in the introduction, about 500,000 customer accounts that we're responsible for restoring power to following a major storm event. And we have a zone storm center located here in Wilmington that we execute all of that process from. And so just a little bit of perspective, you know, on a day-to-day basis, we have about 225 Duke Energy linemen and support staff, engineering, other, you know, kind of support and leadership staff, plus around 400 or so native line track contractors, construction contractors that we have working within these 11 op centers, 16-ish counties on a normal day-to-day basis. When we get into one of these storm restoration, you know, situations, and you know, I think Florence out of the last several years was the most significant of these, that workforce grows to between 5,000 and 7,000 line technicians plus support for those line technicians working within this same geographic area restoring power. And so that is a huge undertaking that goes into that. And that's what we'll just try to dig a little bit deeper into what that looks like and how do we go about executing that restoration process. And so, of course, the first step to that is the preparation. And so, going into a major storm event, and, we do this every year. We're in the midst of it right now as we're getting ready for, the meat of hurricane season here later this summer, is a comprehensive storm response plan. So we have, org charts and structures in place so that everybody in the company understands, when one of these events happen, what are your roles and responsibilities? Where are you expected to respond and be a part of that restoration process? From a forecasting and damage modeling perspective, this is really critical as we go into getting ready for a storm event. Duke has an in-house group of meteorologists, and they have a forecasting tool that they use, so they're obviously taking inputs from, a variety of National Weather Service, NOAA, all those other different agencies, and taking data elements, data points, data inputs from them and running that against resource modeling that we've developed in order to help understand and prepare for what kind of storm impacts might we have based on the forecast, what kind of damage could we expect, how many resources would it potentially take to restore all of that damage within a certain time period. And we're using that ahead of the storm to start going into the resource acquisition phases, bringing in resources from other parts of the country, the staging and logistics decisions that we need to make, which I'll talk about in a little more detail on the next couple of slides, where we need to pre-deploy resources ahead of the storm so that we can hit the ground running with restoration as soon as the storm event has cleared. And then how do we go to full-scale deployment of resources following the storm clearing. And throughout this process, communication is key, and I'll talk about that a little bit more, both internally, what that means, and then also how we communicate with our customers. And so to help facilitate this process, Duke actually moved probably about 4 years ago to the incident command system and structure. This was something that was developed by the Department of Homeland Security back a little bit after the year 2000. And, I would expect many of you, here in the meeting may be familiar with this within, your own organizations or agencies. And what this does is it provides a common organization structure, common roles and responsibilities, common communications framework, so that as we work both internally at Duke Energy, we're all operating in the same manner, communicating at the right levels, making decisions at the right levels, but also this really helps to facilitate how we interact with the local and the state emergency management organizations. So this has become really just now an ingrained way of how we set up our response organizations, and then how we staff those, and how we communicate with all of the different agencies external to Duke Energy that become very critical in the event of a major storm. And what that leads us to is a part of this structure, and I think I just wanted to provide a little bit of context around how at Duke, how we evaluate and respond to different levels of storm events, and how that fits in within that incident command structure. And we look at things from a storm event level, from a 0, which would be a day like today, just a blue sky day, and we have a tree fall or a car hit a pole or something like that. That's handled, that's locally, that's isolated outage events. To then, level 1 and level 2 events start to get into your, summer thunderstorms. Maybe you have a strong cold front come through, something like that, that has a larger number of outages, but is not up yet to the stage of a major storm event. Level 3 is where we really start to talk about those hurricanes and other events like that, where we have a large geographic area of damage. We have a restoration time that's a day or frequently maybe many days as we start to talk about a major hurricane. We start to have enormous need for logistics support. We're setting up, base camps. We've got mutual aid support coming in from other organizations in other states. We have all kinds of financial accounting and tracking that has to go along with that to make sure that we're tracking and managing our resources effectively and our funding effectively. And that just becomes a very significant effort that takes resources from all across the company to execute those. And again, that's what we're really focused on here in the discussion today is those level 3 types of events, how we respond to those and go about restoring power following those events. So, one of the things, and I just alluded to it in the previous slide, but, the logistics that are involved in executing restoration following a major event are significant. As I stated earlier, we wind up, here within the southeastern North Carolina area, very likely could wind up with several thousand line construction resources coming in that are not usually working in the area. And in general, this is I know we've got, Wilmington itself, has a lot of hotel rooms and restaurants and things like that. But, a lot of the southeastern North Carolina area is more rural in nature. There's not a huge availability of hotel rooms and other things like that we need in order just to support the feed and caring of all of those resources come in. And so we set up what we refer to as base camps in order to support that restoration process. And so this picture is just sort of a illustration or map kind of illustration of how we would go up about setting up a base camp. Typically, if we go back and look at like a Hurricane Isaias last year or Florence 3 years ago, across those 16 southeastern North Carolina counties, I think we had around 10 to 12 of these different base camps set up across that footprint to help to house and provide material for all of those resources coming in to town. And those varied in size from maybe supporting 150 resources all the way to supporting 1,500 resources at one location. And I've got here on that next slide a picture of that. So one of our primary base camps that we leverage here, and many thanks to the New Hanover County emergency management folks and the Cape Fear Community College folks, we are able to utilize a large area of parking at the North Campus of the Cape Fear Community College here in Wilmington. And so this is actually, drone footage of how this was set up following Hurricane Florence. We had around 1,500 resources housed at this location at peak as we were restoring power. And that was about a week-long restoration process after Hurricane Florence. And, you see in this picture there on the right side is I-40. All of those trailers we've got, here in the middle, we've got tents that are set up for dining areas. These are mobile kitchens and food storage here, and these semi trucks on the right side. And then all of these trailers across, here kind of the middle going to the left in front of the pond, and then also the trailers at the very bottom left of the screen. Those are all sleep trailers that house approximately 32 individuals within each one of those trailers for lodging arrangements. We ran into a lot of challenges following Hurricane Florence. There was a lot of hotels that sustained damage. It was very difficult. I'm sure I'm not showing anything that's surprising, but it's very difficult in a situation like that to be able to find hotel rooms and restaurants or catering. So we have to bring all of that in externally and set this up. So it's, to me, one of the more interesting and really, critical aspects of the storm response process. Yes, going out and getting the people in the field to repair the damage and get the lights on is mission number one. but we've got to have infrastructure in place to make sure those people have food and a place to sleep at night. And of course, I would be remiss if I didn't speak a little bit to the challenges in that aspect that the COVID pandemic has added to this process over the past year. Last year with Hurricane Isaias, this was, really, front and center for us because we were at that point only, 5 or so months into the COVID pandemic. There was a very rigid structure and expectations in place in terms of what we had to do to try to keep all of these resources safely isolated from each other, try to track people's health, check temperatures, doing all of those kinds of things. Just added a whole nother level of complexity to some of those logistics challenges that we dealt with. And certainly, hopeful that if we have to put any of this, process in place this hurricane season, we're certainly in a better place from a COVID pandemic perspective, but, at the same time, not completely out of the woods there. And so that will continue to be a element of how we respond and the considerations that we have to take in order to keep all of these resources safely working and restoring power. So that gives us perspective around the preparation for a storm event, some of the logistics behind executing the storm response process. And then now what I'll do is I'll talk a little bit about how we actually go about restoring power in the field. My favorite quote in the slide deck here, just a little humor for us to lighten things up. If it weren't for electricity, we'd all be watching television by candlelight. People, every year that goes by, we have more and more devices that require electricity, and more expectation of that electricity staying on or getting back on as quickly as possible. And so we just continue to see a lot more urgency in how we assign resources, how many resources we get, and how we go about this restoration process to make it as quick and efficient as possible. And so what I'll do is just talk a little bit about, we've got our diagram here of the electric system. We'll just talk through the different phases of the system and some of the aspects involved with that go into the power restoration steps. Starting, from a generation perspective, we show our nuclear plant here. We can imagine that's the Brunswick plant down in Southport. We've got our high voltage transmission lines going out to substations that are feeding businesses and residential houses and customers and shopping centers. And so each one of those components of the electrical grid, have steps that have to take place in order to restore power, starting from generation to transmission to substations and then out to the distribution lines. And so we'll start just with the big picture view of things. When we have to recover from a major event, and I'll use Hurricane Florence as an example. We had a lot of generation plants offline. We had a lot of our transmission offline. Probably about 3/4 of our customer accounts here in the coastal zone area were offline following the Hurricane Florence landfall, and following 24 hours of the storm sitting on top of us. And so the first step that we're taking is trying to assess, okay, what is the level of damage that we're dealing with? And there's a lot of different ways that assessment occurs. We're looking at both in our transmission and distribution control centers. We've got a lot of information coming in from devices in the field. So, sensors, SCADA controlled devices that can send messages out and say, okay, I'm online or I'm offline. And so, we're using that to understand where is the damage and how many customers are out, and, start start there. We're also, as quickly as possible, and safety plays a big part in this. So, we have to wait for the winds to die down and the storm to kind of clear out of the area. We're getting assessment teams out in the field to begin analyzing the extent of the damage that we have. That's on the ground, teams out driving and walking out lines and right-of-ways looking for damage. You see a picture of the helicopter here on the screen. They're out flying, particularly with our higher voltage transmission lines, flying right-of-ways looking for damage. Do we have a lot of structures down? Do we just have some trees that have blown over and fallen on the lines? What is the magnitude of damage that we're dealing with? What kind of flooding conditions might we be dealing with? And then also over the last, starting probably for the first time with Florence, we started using drones as well as an element of this assessment process, particularly with some of the flooding conditions that we've had. Drones have been very useful to help us get eyes on areas that otherwise would be very difficult to access or restricted to access due to flooding conditions. And so we're taking all of these data inputs to understand what kind of devices are offline, what are we dealing with, and then what is the level of damage that we're actually seeing out in the field. And again, we have to understand very quickly, is this significant structural damage to our facilities, or is it more minor type damage with trees and some wires down and things like that. And all of that drives how we go about assigning resources, these thousands of extra resources we're bringing in, understanding how they need to be assigned, where they need to go work, how many we need, and ultimately how long, we have to make that important decision. How long is it going to take to restore the power from this event? Is it a 2-day event, a 4-day event, a week-long event to get all of the power on? We have to take all of those different inputs and build that into our response plan and the decisions that we make for setting restoration times. And so if we look at the system here on this slide, we start with our transmission lines. Again, we can't start restoring power to individual customer accounts until our generating plants are online and our transmission system is online. We've seen varying degrees of damage to our transmission system, and that's, typically voltages 115,000 volts, 230,000 volt lines. These are the larger towers, larger lines that you see out around the area. But we absolutely do wind up with damage, structural damage, trees, etc. To these lines following a hurricane type of event that they've got to get out, patrol. This is where you're flying in a helicopter for miles and miles of line looking for that damage, and then getting crews in place to get those restored. We've got to, as a part of that, one of the things that's very key is we have to be able to, balance the generation load with how many customers that we can get back online. And so there's this balancing act that our energy control centers manage around generation plant availability, getting the generation plant online, understanding what transmission lines are out or not out, which ones can actually take load, and making all of that picture balance out. So there's a lot of complexity there, from a technical standpoint in terms of getting the system kind of that backbone, that generation transmission backbone up and running again following a major event. And this slide just shows, some pictures, again, just, illustrations of some, damage and what we've seen in past storm events to transmission lines. This picture down here on the bottom left is a really good example of, what we deal with here in, coastal North Carolina. Lawn transmission lines, frequently very difficult to access areas, swampy areas. So you're talking about, tracked equipment and other specialized equipment to a lot of times be able to get in and restore power, restore the damages to be able to re-energize those lines and start the restoration process. And so that's phase one. You know, that's where we have to start, because again, until we get that transmission backbone back where those lines can be energized, we're not able to start restoring power to any of our end customers. I will mention just briefly, as I talk about transmission, we're going to talk more at the end of the presentation around some of the things that we're doing with strengthening the grid and you know, resiliency. You know, we are investing a lot in transmission infrastructure improvements, upgrading structures so that they can withstand you know, higher wind speeds and things like that. So, you know, we're making a lot of steps. I know I'm talking mostly about restoration, but we're also taking a lot of steps to try to harden that system and you know, help to eliminate you know, opportunities here where we might have that kind of damage and outages. So the next step, you know, in the journey here, as we talk about restoring power, is our substations. So these are you know, highlighted here on the map. This is where the transmission, the high voltage 115,000 volt, 230,000 volt transmission lines meet our distribution lines. Our typical distribution lines in this area are 23,000 volts. And so the substation is where we step that voltage down and deliver that power out to all of our end customers. Typically, in a storm event, you don't see a lot of structural type damage with substations. The challenge that we have faced, and we've seen this, I haven't mentioned Hurricane Matthew yet, but if you go back, I guess 5-6 years, Hurricane Matthew and then Hurricane Florence, we have seen two, you know, 500+ year floods that have occurred here in the southeastern North Carolina area. And that does present a very big problem. On the first slide I showed you guys, we had a picture in there of a flooded substation. And that's been a very big challenge for us in some certain areas due to these just, you know, again, these are 500+ year, you know, flood events, and we've had 2 of those now in the last 6 years. And so that's been one of the biggest challenges that we've faced with our substations and restoring power. And one of the things that we've learned and we've been taking action to help to improve this situation is building permanent flood walls around some of our substations. We've also built some temporary flood walls around some of our more vulnerable substations. And we're even going so far in a couple of cases. Whiteville is an example of this. That was one of the ones that we had a lot of flooding issues with. Actually, you know, this is a very expensive proposition, but actually relocating that substation to higher ground. You know, but that's you know, several $1 million project when you're talking about that time of work. But that's the situation where you know, we found that to be the most prudent situation or you know, solution for dealing with that problem. And so you know, once we you know, go through and get the transmission lines back on, and then we evaluate our substations, any damage, flooding, anything like that, checking equipment in the substation after floodwaters recede. You know, we're ready to now get those energized and then move on to the process of restoring power out to the actual distribution grid itself. And so here, you know, this next slide is just a picture. You know, I was talking about flood walls and substations, so just a picture of what that looks like and what we've put in place in some of these areas that are more vulnerable. And so the distribution, and this is really where my focus lies, you know, and this is really the element of the system that, you know, sustains the greatest level of damage in a major storm event, just because it's, you know, there's a distribution line running down every single street to every single house. So it's just a huge, you know, volume out there that's very susceptible to, you know, trees, flying debris, lightning, all of those elements that we have that can cause damage in a major storm event. And so, you know, so we start the process on the distribution system with our, and it, you know, kind of highlight here, where the distribution lines look here on this map. So starting the process, we have to focus on getting our main feeders on, our three-phase, feeder backbones in order to be able to start picking up, customer loads. So that's our first priority in terms of getting resources out, patrolling the lines, assessing our damage, assigning crews, is getting those feeder backbones back on. And particularly, we focus priorities around critical customer situations, our hospitals, our emergency command centers, our police stations, our water and sewer plants. We've got a list of all of those that goes into that storm restoration process, so that we know we're working with our account managers. We know where those are. We're getting a lot of feedback, obviously, if we have any of those types of facilities out following an event, and those are priority number one in terms of restoration. And so once we go through that process of restoring power to the main feeder lines, kind of up and down the major roads, getting those critical customers back on, we then kind of take the next step in the process, and I'll come back to this in a second, is our tap and service lines. And it says the last mile on here, and that's a good analogy for this. So when we look at how the restoration process operates, it takes us this long to get probably the last 10%, 5 to 10% of customers back on, as it takes us to get the first 90% of customers back on. This work of going and restoring the feeder backbones, riding out all the major lines along the major roads, that goes usually fairly quickly. We typically have less damage in those kinds of situations, because they're out in more accessible places away from heavy tree vegetation typically. When you get to that point of going house to house, street to street, getting customer service lines picked back up. We're showing you, here pictures of, transformers, that are converting the voltage from 23 kV down to, 200, 120, 240 volts that we're delivering to a residence. That process is really where the time and labor comes in. And again, those last 5 to 10% of the customers take a lot of time, because now you're dealing with individual service lines down. I have a crew that's going out, and they're putting up one service line at a time, and now they're only getting on one customer, as opposed to getting a feeder back on that may get 1,000 customers back on. We're finding that we have transformers that were struck by lightning, or maybe tree fell on the pole and broke the pole, and so you're getting a crew into somebody's backyard, replacing a pole, replacing a transformer, and it takes several hours, and you got 4 customers back on. And so this becomes the very tedious, time-consuming part of the restoration process. And so we do a lot of modeling in terms of how we plan out the restoration process and where we need to assign resources that understands kind of that paradigm of how many customers are still out, what kind of damage did we have, and therefore how long is it really going to take us to go and as we say on here, complete that last mile of restoration. One thing, I'm backing up a slide that I wanted to just speak to, and I'll talk more about this in the resiliency component of this PowerPoint as well, but is the introduction that we've made of self-healing technology to the grid. This basically, it means that, a part of this process of getting all of those feeders restored is that we do have devices out there that in some cases are able to talk to each other and automatically restore power for us. And we're installing more and more of those devices every year. I think I saw numbers like from Hurricane Florence, these self-healing teams saved around 80,000 customer outages. So, the grid took steps by itself to restore power to those customers without us having to actually roll a truck out and assess damage. So it's isolating where the damaged sections of line are, and then picking customers back up. And so that's really fundamental to how we are working to improve the system going forward, but it's becoming very fundamental to how we restore power and how the system responds following a major storm event. The last element I want to talk about, and this is really important to us, is the communications process that goes along with one of these major storm events. Our customer expectations, anybody that works in any kind of customer facing industry recognizes that every year that goes by, our customers have higher expectations for what information they get, how they get information, real-time information. And that becomes a very important element that is involved in how we execute the restoration process. And that starts pre-event. So we're getting messaging out to customers that, is warning them of the event, starting to give them an idea of what kind of, damage expectations we have, what they might need to prepare for. Then during the event, we're starting to understand the level of damage. After the event clears, we're starting to get out there and assess the damage like we've talked about. And we're using that, so that damage assessment process, it helps us know where to send line resources, to know where the damage is. It helps us to know what the damage is. So when they get there, what do they need to take with them to fix it? But it also helps us to set our ITRs, our initial time for restoration for our customers, and then our ETRs, which is our kind of the second step, estimated time of restoration for our customers. And we're trying to find that balance between providing information to our customers that's usable and meaningful, but having to kind of put that out at different levels. So maybe the first day after the storm, it's letting our customers know, here's our plan for when we can establish and communicate restoration times. And then the next day, it's moving down to county by county restoration times. And then the next day, we're working that back to maybe a device level restoration time. So if you're a customer, you're impacted by this outage event, and the restoration time for this outage event is going to be 11 p.m. on Tuesday, right? And so it's an iterative process that we have to work through, but we try to be very cognizant of those customer expectations, and again, providing as much information as we possibly can at different steps throughout the process. And we've got a lot of technology now that starts to support that with outbound text messaging, websites, et cetera, that our customers are relying on to make decisions. Do I go back home? Do I stay in a hotel? Do I go visit friends and family? Do I need to go unload the refrigerator? We're thinking about all of those things and trying to put ourselves in the customer's shoes in terms of what information they need and how they want to receive that information. So Katie, that's the first, I'll say first half or so of this presentation, a little bit more than half. But it's a good opportunity now if we just want to open it up for any questions about the actual restoration process before I talk a little bit about some of the work we're doing in resiliency space.
All right, we have a couple questions that have come through. Your slide with the staging area for Hurricane Florence, how many personnel are in each trailer?
So during Florence, it's either 32 or 36 bunks that are set up in each of those sleeping trailers. As I talked about, COVID, and last year with Hurricane Isaias, we actually had to go down to like 8 people per trailer and keep it limited to the, so if we had or maybe 10 people. So if you had a crew of people that worked together all day, they stayed in the sleeping trailer themselves, and no other crew went in there so that we were able to eliminate, reduce exposure as much as possible from a COVID risk perspective. But yeah, full staffing, 32 to 36 people in each one of those trailers. And like I said, about 1,500 people were staying there at that base camp at that time.
All right, next question. Can substation equipment be mounted on elevated structures to keep out of reach of floodwaters?
Yeah, that's a great question, and that it's a little bit outside of my area of expertise. The challenge there is that we need to be able to operate all of the equipment from ground level, or at least close to ground level. So the best case solutions, like I mentioned, is in some cases relocating it, in other cases building permanent fences around it. But yeah, really the reason that we don't elevate that equipment higher than we do is that it's important to be able to go in. We've got the controls and operations for all the different types of devices that really need to be able to be approached and operated by an individual from the ground.
All right, great. That's all the questions for now.
Okay, good. Thank you. All right, so we'll just switch gears a little bit and talk some about our grid improvement plans and how this fits in with what we've talked about in terms of preparing the grid for these kinds of major events. And so we've got a lot of drivers right now in place. We've got weather events, which we've talked about for the last half hour. With climate change and everything else going on, that just seems to continue to be a more prevalent trend. We're also, when we think about grid improvement, thinking about our cyber types of concerns. So I'm talking about hey, it's great, we've got all this communication equipment out there, all this stuff that can phone home and say, here's my status and I'm offline or I'm online, but that makes you vulnerable from a cybersecurity perspective. And so we have to constantly guard against that. We saw the impacts that can have on our infrastructure a few weeks ago with the Colonial Pipeline situation. Customer expectations, I've talked about that already, but customer expectations continue to grow. We expect to have more information more readily available at our fingertips. Distributed technologies, I mean, that's dramatically changing the grid and is going to continue over the next 10 to 20 years with continued growth of distributed generation, battery storage, solar, electric vehicles. We've got to prepare the grid to facilitate all of those changes. We're seeing concentrated growth. You look at our metropolitan areas in North Carolina, Wilmington is growing, Raleigh, Charlotte growing a whole lot, and that places strain on the grid and the system. We've got technology that's coming into play, and I'll talk a little bit here about some of the technology that we're implementing within the distribution system that's become available to us. And then lastly, just environmental trends and expectations. I mean, that drives a lot of how we at Duke think about preparing for the future, how we fit in with environmental policies, how that changes the way that the grid operates. And again, you go back 20, 30 years, the grid was a one-way power flow. You had a generation plant and power went out to people's houses. Now that's become a two-way power flow because we've got this distributed generation all over the grid, and that completely changes the dynamic of not only how we manage how the grid operates, but even how we build the grid, what kind of devices we need, how to facilitate the introduction of all of that technology. And so we really look at two different elements with our grid improvement plans. The first being strengthening. So we're trying to do things that will help to prevent outages from occurring, and that can be both physical hardening type work, upgrading poles and lines to things that are stronger, have higher wind ratings. We're introducing a lot of new coastal construction standards that can more effectively deal with salt contamination and corrosion. So it's all of those kinds of things that can help to prevent the grid from having outages. But then we're also looking at the resiliency of aspects of this. We're never going to be able to stop all outages from occurring. And so when they do, we want to be able to get the power back on more quickly, maybe automatically. We want to reduce the number of customers who are impacted by that outage so that it's 300 customers and not 1,500 customers when that event happens. And so both of these two things have to work together to get us where that end goal lies in terms of the grid of the future. And so a big part of that, as I was saying, is this smart thinking grid and this whole two-way power flow concept. We're putting every year putting more and more equipment out there on the grid, where we've gone from analog devices that just operated locally and nobody knew about it, to now hundreds and thousands of devices out there on the grid that have the ability to communicate with each other, communicate back to our control centers, and say, hey, I went out, I had a fault on this phase, and there was this fault current associated with it, so I think the outage is here, or my battery's failing, I need somebody to come out and fix that. We're getting all of that kind of information. And a big thing that does lead to, I talked about in the restoration process, is our self-healing teams. And I've got just a little video here that I'll try to play. Somebody, Katie, just speak up if the sound doesn't come through, but hopefully we're good here, just to give a little bit more perspective on what we mean when we're talking about self-healing and the smart thinking grid. So here we go. Well, it worked earlier. Okay, well, we're going to skip that video now since it decided it does not want to play for me. But really what it highlights is, the fact we have these grid devices out there within our distribution lines that are able to intelligently detect where faults occur on the distribution system, and then isolate those faults and restore power. And so if we have, as an example, substation A and substation B, and there's distribution lines that go between the two of them, with an open point between those two distribution feeders and electronic devices along the way, we have a tree fall on the line, a car run into a pole, all those types of things that happen. Those devices will talk to each other, they'll decide where the fault location was, and get as many customers back on as possible. And what our goal is to try to sectionalize our system down into about 300 customer chunks, and we have some other criteria around that in terms of customer load, critical customers, things like that as well. So maybe it's not 300 customers, but maybe it's a 5 megawatt customer or something like that. But the objective is, again, from a resiliency perspective, now instead of the old way of doing things, when that car hit that pole, 1,500 people were out until I roll a lineman out there to go look at it, assess the damage, go to different devices, open devices, close devices, and it would take an hour and a half to those devices talking to each other and restoring the power within a matter of a couple of minutes automatically, all down to maybe those 300 customers who were left there right in that immediate section of the grid where that damage occurred. So that's the fundamental change and improvement that we are making to our system. And then I'm going to talk about some other, I'll say, sort of unique, projects that we're doing at Duke, particularly here in the coastal area, that we're introducing that help with this hardening and resiliency process. And so the first one of these, so G&W is a manufacturer, one of our key suppliers for our distribution equipment that we work with. And we've worked with them to actually custom develop a underground switchgear for coastal applications. And so a switchgear, as you can think about it, where we have underground lines, underground feeders, that's where those lines terminate and can be opened and closed and isolate sections of the grid. And so we've developed, worked with G&W to develop these. The first ones of these, we've been doing a pretty large scale improvement project on Bald Head Island, replacing infrastructure over there that was, installed when the island was originally developed. Again, go back to, it's all, it's analog equipment. It doesn't communicate. It doesn't automatically do anything. So when the power goes out on Bald Head Island, we're putting somebody in a boat to go over there and start the restoration process. These new switchgear we're installing will be able to do a lot of those steps automatically. But of course, what's unique about Bald Head Island is you are very vulnerable. You have huge amounts of salt contamination, exposure to flooding, storm surge, all of those different elements. And so this switchgear that we've worked with G&W to develop is a fully submersible device. The gear, it's dielectric switching components within the gear that have been tested to 30 feet of water submersion. The communication box has been tested to 6 feet of water submersion. And it's got a lot of intelligence in terms of being able to protect the system against faults, open, close, automatically restore, isolate the power flow for us. So, this has been kind of a unique project that we've had the opportunity to work on, here. And again, we're putting equipment over there, making significant investment, that will prepare for that next hurricane or other major storm event where we wind up under, 10 feet of storm surge. We're also in the process of starting to install some of the same type of equipment in the landfall development. Again, so these are for situations where we have these large underground based electrical distribution system with 1,000+ customers on them. So that's kind of project number one I wanted to highlight. Project number two, excuse me, I hit the button twice, is it's a program that we call fuse replacement. And so this is a new type of device. S&C Electric is the manufacturer for these, and they call it a trip saver. So, the way a distribution protection scheme works on the typical distribution system, if you look at the old way of doing things, you have a circuit breaker and a substation. Then you have fuses out, so you have a feeder backbone, and then anywhere there's little tap lines feeding, neighborhoods, streets off of that feeder backbone, you have fuses. And, so the way the system's designed is for that fuse to blow or melt, burn, whatever term you want to use, and open up in the event of a fault that's behind it, so that you only lose a section of line that has 10 or 20 or 50 customers on it, and you don't lose the entire 1,500 customer feeder. Well, what we find though is that a lot of those faults are actually temporary in nature. So when I say temporary, that means that maybe you had some kind of animal intrusion that made contact with the line and came off, or you have a tree limb that blows across the line and comes off. And so the old way the system worked with a typical fuse is that, the fuse saw that fault current and it blew and the customers lost power. We'd have to roll a truck out there, go patrol the line. Maybe they found something that caused an outage, maybe they didn't, and then replace that fuse and get the power back on. I've seen various studies, anywhere from 50 to 75% of those faults on the electric distribution system are temporary in nature, meaning that something brushed against the line, cleared itself, and the fault went away. But it becomes a permanent outage, the way that we've done things. And so what this trip saver device does is it actually works as like an electronic fuse, and it will locally open, isolate that fault, and try to close back in and see if that fault is cleared. And so we still get the same upstream protection benefits, so that we don't have a 1,500 customer circuit breaker opening up to isolate the fault. But we also don't wind up with a permanent fault unless there truly is a permanent fault on the line, maybe a car hit a pole and the line is down, or maybe maybe a tree fell and is laying across the line, or a tree limb's laying across the line. So then, yeah, that becomes a permanent fault, and we have to roll somebody out there to repair the damage and get the power back on. But what this device allows us to do is, again, 50 to 75% study I saw, specific to the Wilmington area, was about 2/3 of those faults are really temporary in nature. And this device allows us to keep the power on, prevent a truck roll, and just really, so we're utilizing a new technology now that ultimately, will significantly reduce the both the number of nuisance circuit blinks or operations that customers see, and then also reduce the number of permanent outages that we have on the system. So pretty neat technology. We are in the process of installing literally thousands of these devices across that coastal zone footprint. And then finally, one of the project types that we are working on is what we call targeted undergrounding. And this is, I would say, one of the most intensive, costly types of reliability improvements that we make. But in certain cases, we find that this is the most prudent investment that we can make in order to, address significant reliability concerns. And again, going back to hardening the grid so that we are less susceptible to outages in the future. And so one of the big examples where we're doing that, and this is here in Wilmington, is the Keynes Grant development. This was an area that we identified as one of our initial targets for doing this targeted undergrounding because of the magnitude of customer interruptions that we've historically had in this area. Both blue sky days like today, and then the major storm events. It's just an area because of the the age, the tree conditions, the location of our facilities, just all those different elements together that has made it very susceptible to outages. And so we look and say, so over the last 10 years as we studied this, we've averaged 49 outage events per mile within this area of this development. And so that's pretty significant. That's, for every line mile in here, we've averaged about 5 outages every year. And so that's a pretty high number when we look across the system, and made this stand out as a good candidate for this work. And so, we've had in the process, we will have this completed by this year, of converting all of this system, about 620 customers worth, from overhead construction to underground construction. So that's 18, targeted overhead line segments that will now be fed with underground cable, underground transformers, and underground services to all of these customers' houses. We are continuing, as we go down the path of grid investment, we're continuing to use this as one of the tools in our toolbox to help target our most low performing areas from a reliability perspective. But again, this is very costly, and that's, we always get that question, hey, why can't you guys just put everything underground? Well, this project, it's, I think, in the neighborhood of $6,000 to $7,000 per lot or per customer for us to convert this underground. So, do the math on that times 620 customers. That's a lot of money, and not something that we can just go and wholesale convert our entire system to an underground distribution system. But again, looking at those opportunities where we have that historical information of there being very, very high numbers of overhead line faults, and using that as criteria for making the decision on this kind of investment. So that kind of wraps up the second phase of this. Looks like I'm spot on for time at 11:14, so I'm glad that worked out well. But that just gives you guys a little bit of a perspective on the work that we're doing to make our system more reliable, more resilient. And again, it prepares us both for typical, day-to-day situations that occur, as well as those major storm events. So, Katie, I'll go back to you if there's any final questions before we wrap up.
Great, thanks so much, Scott. I don't see any questions. I'm going to give it a minute and see if anyone types any in. To everyone on the call today, just a reminder that your PDH forms for both the morning session and this session will be emailed to you later this afternoon. So if you do not receive that, let me know. And then tomorrow's sessions are again from 9 to 10 and then 10:15 to 11:15. And you have 2 separate links to join those as well. Scott, I don't see any questions. Thank you so much for being with us today. We really appreciate it. And everyone have a great afternoon.
Hey, thank you for having me. I appreciate the opportunity.